Okay, Thankfully it looks like my internet issues have been fixed all day, so can actually proceed. So tomorrow's lecture should happen at the same time as usual, uh, barring any other issues. If there's issues, I'll let you know, even if I'm reduced to having to phone post like I was yesterday. Okay, so anyway, what is it that we were doing last time? We'd begun Laplace transforms, so I hadn't even defined the Laplace transform yet. I just described the process. So the idea, and hopefully by the end of today's lecture, we'll get to at least see some of this. So the idea is that we have an IVP. I want to hit it with the Laplace transform to turn my IVP, my differential equation, into a set of algebraic equations, or a single algebraic equation. And that algebraic equation is something that can be solved in a more low order way than solving a differential equation. And then I push forward this solution to the algebraic equation I get here via the inverse Laplace transform to get a solution to my IVP. So rather than going directly here, I do all this roundabout thing. So after we've seen this, I'll describe why you might want to do this. It turns out that our process is only going to apply to constant coefficient equations. So this is something that doesn't even apply to the variable coefficient equations that we use variation of parameters for. And so you might say, well, why would I ever use this? This one, when you get used to this, for some problems, this can be really quick. So the stuff that you did for key identities or undetermined coefficients, you don't have to do any of that stuff for Laplace transforms. So you follow this process and it spits out the answer. And what's nice is you know that typically with IVPs, when you find the general solution, you still have to impose the initial conditions and solve for the constants. With Laplace transforms, you actually don't even have to do any of that. So you will get the unique solution spat out immediately from this. MATLAB project will be posted sometime over the weekend. Your exam will be posted. I plan to post the exam on Friday, and you'll have until like Tuesday or something to do it. So yeah, I'll post the exam on Friday. Anyway, so how does this work? So one note: we only apply Laplace transforms to constant coefficient equations. Okay. Okay, so that's one limitation. But before I get to this process, I want to first define what a Laplace transform even is. So definition, and this is the Laplace transform of a function. Okay, I'm off camera. So what's the Laplace transform of a function? So if I have a function f of t, our function we're going to say is defined for t non-negative. Then my Laplace transform of f, I'm using the parameter s here. You'll see where that comes in. So my Laplace transform of f is defined to be the integral from 0 to infinity of e to the minus s times t f of t dt. So take a second to go through what it is I'm saying here. To compute the Laplace transform of a function, I integrate that function against this e to the minus s of t, where s is my parameter. It's my argument for this Laplace transform. Right? So t is the variable with which I'm integrating with respect to. So the expression I get out of this will be some formal expression involving s. Okay, since I'm integrating with respect to t. But this is an improper integral, right? So you might want to refamiliarize yourself with how you compute something like this, right? It's improper in the sense that the interval that you're computing this integral over is of infinite length. So how do you actually compute something like this? Well, you compute it as a limit, right? So the idea is that you compute this as the limit as big T goes to infinity of the integral from 0 to big T of e to the minus s times t f of t dt, right? So here's my Laplace transform. Now, it can be kind of annoying to compute the Laplace transform in this way, and in fact, I'm only going to do this for some very basic functions. So I am going to show you some examples of how to compute the Laplace transform, but I want to stress that this is not what you're going to be doing for the most part. For the most part, you are going to be reading off of a table. Okay, so now most of the computing of Laplace transforms that you will do will be done via what are called Laplace transform tables and properties of the transform. Okay, so actually computing these, as I said, you're not going to do it the way that I'm going to do a couple of these examples right now. Okay, so I'm giving you that warning because I don't want you to think, like, if you don't understand the next couple of examples that I do, you don't need to freak out too much, because this is not how you're going to be computing Laplace transforms typically. You're not going to be using the definition. Okay, but anyway, there's the definition of Laplace transform. Okay, so let's do a quick example, kind of the most basic thing. Since the Laplace transform is defined as this weird integrating against this exponential, taking function integrating against exponential, you might guess that the simplest Laplace transform to do is the Laplace transform of an exponential. So that's what we're going to do. So here's an example. Find the Laplace transform of e to the at, where a is some constant, right? So let's say a is just some real number. Okay, so a is a real number. I want to compute this. All right. So then by definition, right, Laplace transform of e to the at of s is, I'm going to go ahead and write it as a limit. This is the limit as big T goes to infinity of the integral from 0 to big T of e to the minus st e to the at dt. Now I can obviously simplify this. So this is the limit as big T goes to infinity, the integral from 0 to big T, using my exponential laws, right? This is e to the minus s minus a times t dt. Okay, just quickly check that that's what it is. This is e to the minus st plus at. So I'm writing it like this. Okay, and you'll see why I'm writing it like this. Specifically, I know that I'm going to be taking this limit, right? And this thing is going to converge exactly where I'm going to. So if you're just thinking intuitively, right, about what this means, you know that this is very much going to depend on the sign of this thing, right? So if s minus a is negative, that's going to be bad, because this is going to be integrating e to positive number on this open interval on the positive reals. That's clearly going to go to infinity. It's going to diverge. And so you're actually going to want s minus a to be positive, right? So you want s minus a to be positive and not negative here. That's just intuitively looking at this thing, but let's compute this out. So How does this work? So first of all, make an assumption. If s is equal to a, then this is 0, and this is the limit as t goes to infinity of 0 to t of 1 dt, and that's clearly infinite. So notice this. Let's suppose that s is not equal to a. Note, if s is equal to a, this integral is infinity. Again, why? If s is equal to a, this would be e to the 0t. Well, that'd be e to the 0, which is just 1. So this is the limit as t goes to infinity of 0, the integral from 0 to t of 1 dt, so that's infinite. Okay, that limit's infinite. Okay, and so we're assuming that s is not equal to a. So then how does this break down? What is the integral of this thing? Remember your substitution, right? How does this go? This is the limit as big T goes to infinity of, this is going to be s minus a. So this is, or minus e to the minus s minus a t over s minus a. And that's evaluated from 0 to big T, right? Okay, so this is the limit as big T goes to infinity of, because of the minus sign here, I'm going to keep it as a minus b. So this is going to be 1 over s minus a minus e to the minus s minus a times big T over s minus a. So it's this expression. Okay. Well, this first term doesn't depend on big T at all. So that's fine. This second term definitely depends on big T. And what is this limit? What's the limit of the second term? Well, it depends on s minus a, right? So note, if s minus a is positive, then this is minus a positive number times a positive number. Big T is positive, right? So this is e to some negative thing that is going off to infinity, right? So this is going off to 0, right? And s is not equal to a, so we don't have to worry about these denominators. And so if s minus a is positive, this term goes to 0, and this is equal to 1 over s minus a. So this is equal to 1 over s minus a if s minus a is positive. And there's another case. If s minus a is negative, well, then the opposite of what I said is true, right? This is e to some very positive number, which is going off to infinity. So this is infinity if s minus a is negative. But s minus a being positive means, another way of writing that is s is bigger than a. And another way of writing s minus a as negative is saying that s is less than a. Okay? And so we've characterized what this Laplace transform is for all these different values of a. Okay. And so it is either, if s is equal to a, it's infinity. If s is bigger than a, it's 1 over s minus a. And if s is less than a, it's also infinity. And so the way that we define the Laplace transform is we say that we only consider this thing having a Laplace transform wherever this is defined. We don't care about infinity. We toss that out. And so this is actually only defined for some particular s values, s bigger than a. And so the way we would express this is the following. So the Laplace transform of E to the AT of S is 1 over S minus A for S bigger than A. It's not defined for other S values. All right, so that's an example of how you would compute a Laplace transform. So this is an example of how you would compute a Laplace transform for or using the definition directly. Okay. So shouldn't it be minus infinity? No, I don't think so. Oh, you're saying because of this minus sign here? Yeah, it's fine. I guess it should be minus infinity. It doesn't matter. We don't care as long as it's not. If it's undefined, if it is infinite or minus infinity, it doesn't matter. We're not interested in it. So yeah, we're only interested when that thing actually converges, when that limit exists. Okay, so let's do one more example, and then I will shortcut the rest of the examples. So here's another example. So compute Laplace transform of, we'll say t e to the at s. Okay, using the definition. So Laplace transform of t e to the at of s is the limit as big T goes to infinity, the integral from 0 to big T of t e to the at times e to the minus st dt. Okay, so rewriting this in the same way that I rewrote the other. This is the limit of that integral from 0 to big T of t times e to the minus s minus a t dt. Okay. Here I integrate by parts, right? So integrate by parts. So integrating by parts. Remember, when you integrate by parts, just a quick thing to remember is whatever is your, if you're doing integration by parts in terms of u and dv, u is the thing you want to be simpler when you take its derivative, and dv is typically the thing that you're just happy to be able to integrate. So so here, if you let u be t and dv be e to the minus s minus a over, or times t dt, then what do you get here? So this is the limit as big T goes to infinity of so this would be the t, so if u is t, right, so if you're integrating by parts here and u is t and dv is e to the minus s minus a t, you have u v. V is going to be 1 over s minus a, or sorry, minus 1 over s minus a. So this would be the limit as of minus t over s minus a minus, and then you get 2 of those coming from the second integral, because the second integral is only going to involve so v here is going to be minus 1 over s minus a e to the minus s minus a t, right? That's our, if this is dv, then this is our v. Okay, and so this is minus t over s minus a minus 1 over s minus a squared all times e to the minus s minus a t. And this is evaluated from 0 to big T. Remember, in this case, you're integrating with respect to t, so this evaluation occurs in the t, not the s. Okay. And so, doing this evaluation here and regrouping. So when I plug in 0, the only term I get So plugging in 0 here yields a 1. Plugging in 0 here yields a 0 for that term. And so, and I'm subtracting, so I have minus 1 over s minus a squared. So I have 1 over s minus a squared as my 0 term. And then my big T term is, I'm going to go ahead and factor out that minus here. That big T term is minus big T plugged in for little t. S minus a plus 1 over s minus a squared, all times e to the minus s minus a big T. Oh, I forgot to write my limit. Let me give myself some room here. So this is the limit of all this stuff as big T goes to infinity. Okay. So it's good that this big T, of course, is grouped multiplying this exponential thing. So how is this going to work out? Again, it's going to very much depend on the relative size of s compared to a here. So if s minus a is positive, we're good because this entire term is going to go to 0. And if s minus a is negative, we're bad because this entire term blows up. Okay, and so this is equal to, in the event that s minus a is positive, and this term goes to 0, I'm left with just 1 over s minus a squared. So this is 1 over s minus a squared if s minus a is positive, and infinity if s minus a is negative. Okay, and so we have again found the Laplace transform where this limit actually exists. So Laplace transform of t e to the at of s is 1 over s minus a all squared for s bigger than a. Okay, so that's my Laplace transform. Now, you could see how this would get really annoying really quickly. Thankfully, this is not how you're going to actually compute these things typically. Okay, but this is how it works. I'm going to mention one more thing. I'm not actually even going to compute it. I'm just going to show you. It's very straightforward actually, based on what we just did. Another quick example. I'm just going to state it. So the Laplace transform of e to the IVP of s is actually 1 over s minus IB for s positive. This is actually, if you're interested in this is done in the exact same way. So it's done in the exact same way. Just pretend like when you're introducing the I, it's a constant in the sense that you were used to doing integrals that involved real constants. So doing that, you end up with this. And you might say, oh, I'm a little uncomfortable doing that. This is like a purely formal object, right? So this is like the height of symbol pushing, if you like. You're proceeding as if everything is working out okay, only worried about the details when you need to, really. Okay. So the reason I wrote this is we're actually going to use this to figure out Laplace transforms of cosine and sine later. So it turns out, as I said before, it turns out that the best way to deal with Laplace transforms is to use very few basic identities together with properties of the transform. Okay, so it's the properties of the transform that are very nice. So what is property? So property one, it's linear. This might not be that surprising to you since the Laplace transform is defined as an integral of something, and you know that integrals are linear, right? So what does this mean? If L of f of s and L of g of s are defined, then so is Laplace transform of f plus g of s. And guess what? The Laplace transform of f plus g of f is the Laplace transform of f plus the Laplace transform of g. Okay, so it is linear, okay, in this way. Okay. All right. Also, if c is any constant, the Laplace transform of c f s is c times the Laplace transform of f. And so it's not some like, almost linear thing. It is truly linear in the sense of splits across sums. I can pull constants out of it, so it is linear in the, I'm off camera. It is linear in the sense that you're used to the word linear. Okay. So what's a way of coming up with Laplace transforms using, say, linearity? So here's an example. I can use linearity of the Laplace transform to compute. Hold on, let me readjust my camera. There we go. There. I can use linearity of the Laplace transform to compute Laplace transform of cosine of bt and Laplace transform of sine of bt. Okay, for any b not equal to 0. So b is some real number not equal to 0. All right, so how does this work? Okay, recall the Euler formula. All right, so Euler formula says that e to the IBT is equal to cosine of bt plus I sine of bt. Right? This is just the Euler formula. So instead of e to the I theta, theta is bt here. So there you go. All right. So there's our Euler formula. Thus, by linearity, why did I use the Laplace transform L to write linearity? So by linearity, if I look at how should I do this? I can view oh yeah, that's the best way to do it. So I can view cosine. So this isn't really true by linearity. This is just true in general from the Euler formula. So from the Euler formula, cosine of bt is e to the ibt plus e to the minus ibt over 2. And sine of bt is e to the ibt minus e to the minus ibt over 2. Okay. Now, so since this is the case, I can recall that the Laplace transform of e to the IBT was, I have it on the previous page. This is Laplace transform of e to the IBT. So Laplace transform of e to the IBT is 1 over s minus IB. Okay. And so Laplace transform of cosine of bt using these two things is 1/2 the Laplace transform of e to the IBT plus 1/2, or I should say minus 1/2 if you're like, or Laplace transform of e to the minus IBT here. Here, I suppress the s there. Okay. But I know what this is just by this above formula. This is 1/2 1 over s minus IB plus 1/2 1 over s plus IB. Doing some quick complex arithmetic, right? Inverting both of these, right? So finding what 1 over s minus IB is and 1 over s plus IB is. This actually becomes s over s squared plus b squared. And similarly, I look at the Laplace transform of sine of bt. This is 1/2 Laplace transform of e to the IBT of s minus 1/2. Sorry, this is technically an I over 2 here. I forgot this expression is wrong here. So this is an I over, or sorry, this is a I times 2 in the denominator, or 2I in the denominator. So this is 1 over 2I Laplace transform of e to the minus IBT of s. So this is, again, with some complex arithmetic. So this is 1 over 2I times 1 over s minus IB minus 1 over 2I times 1 over s plus IB. And it turns out that if you go through all of that, this is b over s squared plus b squared. Okay. So if you found that slightly confusing, don't worry too much. Again, as I said, you're not going to do a computation like this. If you need to find the Laplace transform of cosine of bt, you're just going to say, oh, that's s over s squared plus b squared. Okay, so in summary, thus the Laplace transform of cosine of bt of s is equal to s over s squared plus b squared, and the Laplace transform of sine of bt of s is equal to b over s squared plus b squared. Okay. Now you might say, oh, and you could say, like, for what values is this true? Recall going back to so I had that this was the case for s positive, so the same restriction here holds. This is true for s positive. Now you might say, why are you going through all this if we're just going to read these off from a table? I just don't want the entries in the table to seem like they came out of nowhere, right? I want you to at least know how this is going to work. Yeah, so answering your question, Ashley, since you're going to get the Laplace tables, you don't need to know this derivation process. All you need to know is this. Okay. Knowing the linearity does help in some of, I mean, okay, you are going to have to use the linearity regardless. So that little trick that I did is something that you're going to do in the problems themselves. But you're not going to do it to figure out what the Laplace transform of cosine and sine, what these Laplace transforms are. You're not going to do that. You're going to know that. So the Laplace transforms that you are going to have to compute are going to be some combination of functions you can't directly read off the table. You have to use the properties. You'll see what I'm talking about when we do a couple of examples. Okay, so anyway, continuing on. What's another fact? So the other fact, the textbook goes over hyperbolic cosine and sine. You don't need to know those. I mean, in the sense, I believe they're included in the longer table in the chapter. So in that sense, you don't really need to know any of these, as I said. But property 2 that is important. Okay, so this is a very important property of Laplace transforms. So multiplication, it's best thought of in the following way. So multiplication by an exponential in t is a translation in S. So multiplying your function that you're computing the Laplace transform of by an exponential in t yields a translation in S. Okay, what does that mean? So here's exactly what it means. If you have a Laplace transform L of f of S, and this thing exists for all S bigger than some number. The textbook uses alpha, so that's what I'll use. And if A is any real number, then the Laplace transform of e to the at f of t of S exists for every s greater than alpha plus a, and the Laplace transform of e to the at f of t of S is equal to the Laplace transform of f translated by a. So instead of an s being here, I am plugging in s minus a, which if you're, go back to like pre-calc for a second. If you have function f of x, then f of x minus a is a translation, right? A units to the right if a is positive. Okay, so this is a translation in some way. Okay, so I'm not going to prove why that is, but this immediately tells us how to compute some more complicated things, right? So above here on the same page, I know the Laplace transform of cosine of bt and sine of bt. So then this is going to allow me, this fact is going to allow me to compute the Laplace transform of e to the at cosine of bt and e to the at sine of bt. Okay, in fact, let's do that on the next page. So this expands our list of Laplace transforms. This allows us to expand our list of Laplace transforms. So I have the Laplace transform of e to the a times e to the ibt, right? So I'm going to go ahead and combine those. So e to the a plus ibt of S. So what is that? That is 1 over S minus a minus ib, right? For s, normally it was bigger than 0, so it's s bigger than 0 plus a, so that's s bigger than a. Okay, and Laplace transform of e to the at times cosine of bt of s is, well, recall the Laplace transform of cosine of bt was s over s squared plus b squared. So by this translation fact, I just take this and translate by a, right? I plug in s minus a for every instance of s here. And so this becomes s minus a over s minus a squared plus b squared for, again, s bigger than a. I have Laplace transform of e to the at sine of bt of s. Remember, the Laplace transform of sine of bt was b over s squared plus b squared. And so this is b over s minus a squared plus b squared for s bigger than a. Okay. The textbook goes over the formulas for hyperbolic cosine and hyperbolic sine. I'm not going to list those. You can have a look at those in the section yourself. But this is just further. This is more generalization of the Laplace transforms that we can actually compute. Okay. Definition of linearity. Yeah, definition of linearity is basically that it splits across sums and you can pull constants out of it. So Laplace transform of a sum is the sum of the Laplace transforms, and Laplace transform of constant times function is constant times Laplace transform of function. Okay, so the idea is, I mean, I should say that whether or not we had online classes or not, you were going to have a Laplace transform table regardless. So I was going to, it is customary for 246 students to get access to Laplace transform tables for the exam that you're about to take that includes Laplace transforms, as well as the final exam. So that was going to happen regardless. You're always going to have Laplace tables, but that's why I can, here's my, my 30-year-old boomer story, where back in my day, when I was in 246, or the equivalent of 246, I didn't get Laplace transform tables. I had to memorize a table of Laplace transforms. So you all are like really, really lucky that, we are so nice that we give you tables of Laplace transforms, because you could totally, I think it wouldn't be that horrible to force you all, to grind through the memorization of a bunch of Laplace transforms. But it's okay. We're nice these days, so we're not going to force you all to do that. Like I said, even if we actually had physical classes, we wouldn't force you all to do that. So I'm going to note one more thing here. So before mentioning where like the master list of Laplace transforms are in your notes. So one more thing, let u of t equal the unit step function or Heaviside function. I want to say that I think this is true of Heaviside. I think, if I'm not confusing him with someone else, Heaviside was a pretty cool guy, because I think he didn't actually start learning anything about math until he was like in his 40s. So he was definitely a late bloomer, which is rare, but shows that it can definitely be done if you feel like it. Oliver Heaviside, I think his name was. Anyway, so the Heaviside function, what is it? So it's the function that turns on at 0. So it is 1 for t greater than or equal to 0, and 0 for t less than 0. Okay, you can think of it as a switch, right? It turns on at t equals 0 is when it turns from off to on. Okay, so it is the piecewise step function defined in this way. Then u of t times f of t, of course, is f of t for t greater than or equal to 0, and 0 else. Right? Okay. All right. So what does this mean? Furthermore, u of t minus c times f of t minus c is equal to f of t minus c for t minus c greater than or equal to 0, but that another way of writing that is t greater than or equal to c. Right? And 0 else. Right? This is a way of, if u of t turns on at 0, u of t minus c turns on at c. Right? And so that's a way of writing this. Okay. All right. So then there's the following fact. Okay. That the Laplace transform of u of t minus c, and this is true wherever it's sensible. I'm not going to write the hypotheses here. So the hypothesis is just that the Laplace transform of f exists. This Laplace transform of this function I've written here, this shifted function that turns on at c. What is this? This is e to the minus cs times the Laplace transform of f of s. What is this? Looks a little confusing. So what is it that I'm going to say here? The Laplace transform turns a translation of t, that's this thing, into multiplication by an exponential in S. So this is just the converse direction, or the other side of what I was saying previously about that second property, right? So let me go back for a second and remind you. We had property 2. Okay, property 2 says that multiplication by an exponential in t is a translation in S, and this was the thing that expressed that. So the Laplace transform of e to the at f of t of s is Laplace transform of f that has been shifted in this way. Okay, conversely, I could say this is property 3. In fact, I'll say, if you like, this is property 3, even though it's really just property 2 in another light. So this is that the Laplace transform takes a translation of t into multiplication by an exponential in S. Okay. All right. And it is on account of the Laplace transform behaving well with respect to Heaviside functions that one of the main applications of Laplace transforms that make them useful compared to key identities or undetermined coefficients is that, so I should say idea here, maybe. Idea. The Laplace, I like that. Laplace transform behaves well with respect to piecewise functions. Okay. Now, here's something. I haven't uploaded that supplemental lecture yet. I'm going to do that for undetermined coefficients and talk about some other of these things. But just know it's like entirely extra. It's not needed. But something that I didn't mention very much was for key identities and undetermined coefficients. What happens if the forcing function on the right, your right-hand side function in the non-homogeneous case, what happens if that function is not quite in characteristic form? What if, for instance, it's a sum of a couple of functions that are in characteristic form? What that means is that you would have to do that process of key identities or undetermined coefficients. You would have to do it twice. You would have to do it, or not just twice, if it's a sum of three things, each of which are in characteristic form, but they're in different characteristic form, you would have to repeat that process and then sum the end result. So however many pieces there are in that function, you would essentially have to repeat the process, okay? That's if you have something in composite characteristic form. Another thing is, what if the right-hand side function is actually... say a piecewise function, right? This is something that we didn't really deal with yet. Well, it turns out because of this fact that the Laplace transform behaves well with piecewise functions in this way, the Laplace transform has no issue with forcing functions that are piecewise. And so this is the main strength of the Laplace transform compared to the older methods that we did. But unfortunately, due to time constraints, I'm not really going to talk too much about that. So if you want to see that stuff, so 9.9 in chapter 2 is where that stuff is. Okay, 9.9 in chapter 2 explains how you go through that process. Now, like I said, I would have done that in a normal class, but due to all these constraints, I'm not going to do this. Okay. So, what are we leading to? As I mentioned before, in our evaluation of key identities, we're not going, key identities of Laplace transforms, we are not going to actually compute. We're going to read from a table. Okay, so the ultimate Laplace transform table is on page, I believe it's 37 in chapter 2, section 9. Okay, so it's page 37, chapter 2, section 9. This is the ultimate Laplace transform table. It's the only one you need for any problem that you do in the book. Okay, or on an exam or anything. This is the only one that you're going to need. Okay, so how do we actually apply any of this to actually solving stuff? So there's one more property of Laplace transforms that we need. So we need one additional property of Laplace transforms before we can actually apply anything. Okay. So what is this one additional property? So suppose y is a function of t with enough derivatives. And what I mean by that is it has enough derivatives so that the expressions I'm going to write out make sense. Okay, so if I want it to be a twice differentiable function, then I'm only going to write expressions that involve up to the second derivative. But anyway, it's got enough derivatives. Okay. Here's some notation that is going to be used throughout all of our dealings with Laplace transforms. So here's notation. The Laplace transform of our little function, or our function little y of s, we define that to be big Y of s. Okay. So this is defined to be big Y. Okay. Now, what is the property that I'm talking about? Okay. So suppose y has enough derivatives, then L of y prime of s, that is the Laplace transform of its first derivative, is s times the Laplace transform of y of s minus y of 0. So for this fact, enough derivatives just means 1 because I'm only talking about this. Okay, so this is Laplace transform of the derivative of a function. I can write it in terms of the Laplace transform of the function. And so simplifying this becomes s of big Y of s minus little y of 0. Okay. Now, I want to iterate this over and over again. What do I mean by that? I want to apply this to the second derivative. I want to apply this to the third derivative, fourth derivative, and so on. That's why I'm going to require that this thing have enough derivatives. Okay, so applying this fact over and over again. So applying this fact repeatedly, I begin with Laplace transform of little y is big Y of s. And by that fact, Laplace transform of little y prime of s is s times Laplace transform of little y of s minus y of 0. But that is, this is big Y, right? This is s big Y of s minus little y of 0. Okay. Applying the formula again, this is L of y double prime of s. According to this first formula, using y prime in the place of y, this is s times the Laplace transform of y prime of s minus y prime of 0. But now I use this previous formula for this thing. So this is s times s y of s minus y 0, or y of 0, minus y prime of 0. And so this becomes s squared big Y of s minus s little y of 0 minus y prime of 0. Okay. Practically speaking, this is as far as you have to go. Okay, so this is all you need, practically speaking. The reason I say that is that you might have already seen that we're going to apply this to IVPs, and so we're going to apply this to IVPs that are second order. That's why we only need up to the second derivative. And so, summarizing all of this, if we say that L of little y is big Y of S, that's our definition, then L of little y prime of S is S big Y of S minus little y of 0, and Laplace transform of little y double prime of S is S squared big Y of S minus S little y of 0 minus y little y prime of 0. So this is all you need. You can continue this pattern for higher derivatives, but this is all we're going to use. Okay. And so I'm going to draw a diagram, and we're going to be done for today. And then tomorrow in lecture, I'm literally from the beginning of the lecture till the end, I'm going to do nothing but examples. Okay, so tomorrow's lecture is going to be nothing but Laplace transform examples, because none of this will quite make sense until you see a fully worked example out, but unfortunately this is needed as the build-up. Okay, so finally, how do I actually use this to solve an IVP? So finally, how do I use any of this to solve an IVP? Okay. So here is the process. I have an IVP. Okay. This IVP is Ly is equal to f of t plus initial conditions. That's my IVP. Okay. I hit this with the Laplace transform. Okay. This gives me algebraic equations. The form that these algebraic equations are in is P of S, which is the characteristic polynomial. I'm actually spoiling some of the fun here. This is characteristic polynomial times big Y of S minus Q of S, that's some polynomial, is equal to big F of S. This is the algebraic equation I get. It's always going to work out like this. Big F of S is, as you imagine, the Laplace transform of the right-hand side here. Okay, so I solve for big Y. Remember, big Y of S is the Laplace transform of little y. That's my unknown function. That's what I'm solving the differential equation for. Okay, and so what I get is solution to algebraic equations. Right? My solution, just formally, right, just solving this, so adding Q of S to both sides, dividing by P of S, is Q of S plus big F of S over P of S. Okay. So I started with an IVP. Now I have hit it with the Laplace transform to go to algebraic equations that look like this. They always look like this. I solve these algebraic equations for big Y of S. That gives me this. How do I get little y, which is what I seek? I hit big Y with something called the inverse Laplace transform. And what that gives me is solution to IVP. And that solution is little y of t, which is the inverse Laplace transform of big Y of S of t. Okay. Now this is the same diagram I had when we first started, except now I've actually filled in some of these things with expressions. This is the notation we're going to use. Now maybe that this doesn't help you see how this works. I'm going to go through the process here tomorrow when we do this, and like I said, I'm going to do nothing but a ton of examples to show you how this works. Okay, so let me see if I have any last minute questions here. Yeah, I'm still planning a lecture on undetermined coefficients. I'm going to try to record it later tonight. The problem is I've been having an issue finding a place to record because like everywhere that I would have normally used to record is closed, and I will get run off even if I do it at like 3 a.m. because I have attempted. So I will I will figure out a way to make it work. So anyway, that's the plan. But yeah, I'm going to upload that. So there will be tomorrow's lecture on Laplace transforms. I'm going to try to upload the undetermined coefficients supplemental lecture soon as I can, although it's not needed for the exam. Then I'll post the exam on Friday. So that's the idea. I'll post the MATLAB project sometime over the weekend. I wouldn't worry too much about that. You can work on it on your own. It's not going to be due till the end of the semester, so it'll be due like last day of classes or something. And anyway, I believe that's it. So gonna end the stream, and I will see you all tomorrow during lecture. So we'll finish Laplace transforms for sure tomorrow, and that way you'll have everything you need to know for the exam. So the exam will be chapter. It'll cover all of chapter 2. Okay, and like I said, you'll have till I'll post it on Friday. You'll have till like Tuesday or something to do it. So. Anyway, that's it. So I'll see you all later.